Now let's look at this figure 20-41. Now this deals with the conductors over 25 foot up to 100 foot on the secondary side of the transformer that you see in the illustration. The primary now, we have a 150 amp set of fuses, and we're taking the sizing of the overcurrent device at 150% or less of the secondary to primary ratio in accordance with 240.92C1, item 1. Now what they're talking about here is in the illustration where you have 13,800 primary voltage. Secondary voltage is 480. So when you look in the third set of calculating values, look at calculating amps at fault. Then you drop down to that third bullet and you see 13,800 volts divided by 480 volts gives us a ratio of 28.8. Now with that information and the design tip, you can read it in more detail. But basically, I'm wanting to call up out of this design tip 2500 kVA, 5.75%. Divide that by 100, and then you would come up with 0.00575 would be your divider there. And then the resistance of the secondary side of your conductors, as outlined in the design tip, you have a resistance of 0.001819, another resistance of 0.005295. And when we add those together, we will come up, as you see in the, starting at the top, calculate secondary FLA, calculate secondary short circuit, and then calculate at fault. Then you look at that total resistance of the transformer and the cable bus, then you see we come up with 0.007114 is our total resistance. So, those are the things that we're kind of important in. But you're basically taking, 277 volts to this ground to get your resistance that we're looking at there, see. But you get all that information right here in the design tip. I'm just breaking it down a little faster for you, but you can look it up and calculate it yourself if you want to. But now remember, we're looking at conductor taps over 25 foot up to 100 foot now, based upon transformer secondary conductors. And we're in supervised industrial locations. Usually that means, you have supervision to ensure we have qualified people that will service this installation you see in the figure. And usually they have an engineering staff aboard. You want to be qualified to do this, and most time engineers would do this. But as a basic calculation here, calculating the secondary FLA, then you'd have 2500 kVA, the size of your transformer, times 1,000 to get it into VA, divided on the secondary now by 480 times the square root of 3, we come up with 3008 amp. Now to determine what the short circuit current would be at the transformer, we would take 3008 amp divided by 0.0575, we'd come up with 52,313 amps of short circuit current. Next step, calculate at a fault. So the transformer now has a resistance, as we see in the call out information, of 0.005295. The cable bus has a resistance in the information in the design tip, if you want to dig it out, 0.001819 is your resistance. Now those added up we come up with a 0.007114 as our resistance. 480 now, and the 13,800, we come up with a 28.8 ratio. The primary now voltage that we're going to look at, we're talking about phases. We'd have 277 volts to ground on that 480, 277 volt side is what I'm saying. Now you take that and divide that by 0.007114, which is your resistance that you see totaled in the calculation at the fault that we just performed. Divide that into the voltage, and we come up with 38,933 amps would be the fault current there based upon the ratio. Calculating primary now, we got to get enough voltage from this ratio to trip that 150 amp fuse. That's what we're trying to perform here. So calculate the primary short circuit current. You would take the 38,933 that we just calculated, divide that by 28.8, and you'd come up with 1,352 amp. Now, we need 5 to 6 times that primary rating of that fuse. So let's just say 6 times. 6 times 150, then that would be 900. So the note says yes, the 13,052 amp clears a 150 amp fuse. So we could make the over 10 foot up to 100 foot tap here. And then, of course, next we're going to look at a basic calculation coming up for any length you wanted. And, you know, that hasn't always been in the code, but it is now. So that's what this figure that we're looking at, 20-41, is illustrating. When you make a tap over 10 feet or 25 feet up to 100 feet, and then you can see the calculation procedure to see if you have enough fault current, short circuit current, occur, if that happened, to trip that 150 amp set of fuses that you see in the diagram.